एंड ओके एंड थोड़े बहुत क्वेश्चंस भी देखेंगे जो कंसेप्ट वाइज इम्पोर्टेंट है एंड इंटरव्यू वाइज भी इम्पोर्टेंट है. सो बिफोर स्टार्टिंग, अगर आपको कोई भी डाउट है तो प्लीज विदाउट एनी हेजिटेशन speak up, okay? Or I'll be also coding, right? And you guys will be also coding along with me. So I'll be checking on you guys, and you would have to react if you are with me or not, okay? So just actively participate in the event as well, okay? So let's start. So basically graph क्या है, ठीक है? तो graph is nothing but a set of vertex, like a set of vertices, and like those vertices can be like this, right? And they are connected with each other, right, through edges. So this is known as vertex, right? And these are the edges, right? So your graph can look like anything like this or this, right? Like a Christmas tree, anything, right? Or it can be even a single vertex, right? So graph is nothing but a set of vertex that are joined with edges, okay? Right. And what is a tree, right? The tree is nothing but a graph, right? Which has n vertices, right? N vertex, and it should have n minus 1 edges, right? So a tree is nothing but a graph. Let's say this. So this is my tree because it has 3 vertex, right? 1, 2, 3, and it has 2 edges, right? So we can call it as a tree, right? There are again several differences between tree and graph, but this is the simplest one that you can remember, right? Okay. Now, before we get into this more, why do we study graphs and trees, right? So, like, there are several applications of these data structures in um, in everything we use in our daily life, right? Let's say you use Google Maps, right? So Google Maps use graphs and graph algorithms to determine, you know, the distance and everything. You also might use Uber, right? Uber, Google Map. So it's pretty important to have these concepts in mind, because if you are going to work in uh, if you are going to work on any product, right, then this concepts are pretty useful and important in every other thing that you will come across, right? So let's again come back to graph, right? So as I said, graph can look anything like this, right? uh, so there's basically uh, a root node, right? But it is not in the graph, it is in the tree. A graph can be anything without even a root node. But let's say we are talking about a tree. So there's always a node uh, which is connected to other vertices, right? And this is known as the root of the tree, right? And a root does not have any incoming edge in it. right? No incoming edge, right? Whereas a graph can have like no root. It does not have any specific kind of node, which can be called as a root, right? And let's say this is our graph, right? So this, I'll just change, right? This, this node and this node is known as the child of this node, right? So this node then becomes the parent, right? And these two are the child, right? Similarly, these two guys are um, child for the specific nodes, right? So there are basically, wait, I just, okay. There are basically three kinds of graphs that are important, right? The first is a directed graph, right? So as the name suggests, suppose we have our graph like this, right? So there is an arrow from either one node to other, right? So this is known as a directed graph. And what the arrow suggests that there is a path from this node to this node, right? But you cannot go from this node to this node. It is not allowed, right? Similarly, you can go from here to here, but you cannot go from here to here. Then there is undirected graph, right? So as the name suggests, not there are not any arrows suggesting that you can only go from here to here. You can go in both the directions. It's bidirectional. So assume like the edges are like this. You can just even present them like this without any arrows, right? And the third one is weighted, right? And along in weighted, there are again this undirected and direct, right? So what is weighted? Let's say there is this node, this graph, right? So 2, 3, 1, and 4. So there are certain values on each of the edges, right? They can all be even same or they can be different. And these values represent the weight, right? So you can consider them as a distance between each node, right? So let's say you are currently standing here, right? And this is your home. And there are several other things between your home, right? Like this. And you need to calculate like what's the least time you can get to your home. Uh, Consider this as distance between each of the uh, places, right? So in this case, like the weighted graph comes into part, and you need to again find out what is the least distance from here to here, right? There are algorithms for that again. So um, we can, okay. Now, if we want to traverse a graph, right? There are again two methods for that. But before that, I'll just write them here and we'll get back to that. So like, how do you, how do you present a graph, or you store a graph in terms of code, right? So again, there are two methods of storing, right? The first is using adjacency, sorry if the spelling is wrong, matrix, and another is list. So there are a few pros and cons of each of these methods of representing the graph, right? Let's say I have a graph, a simple graph like this, and I'll just number the vertices, right? So let's say, consider each of the node like this, right? And you can build a matrix, right? For that, let's consider the matrix, right? So if I want to, right, let's see. So there's an edge between 1 and 2, right? So I'll just locate 1 and 2. So let's say it's this part. So I can just write 1 year. So that's represent that there is an age between 1 and 2. Similarly, I can write a 1 between in year, right? Because there's this undirected graph and you can travel from 1 to 2 or 2 to 1. If there was a directed graph, then you should not write in each of the places 1. You should first look where the arrow is pointing, right? Similarly, we can write for 1 and 3 and for 2 and 4, right? And 2 and 5. So there's one thing. If somebody asks me, like, okay, tell me if there's an edge between node X and node Y. I want to tell if there is an edge between X and Y. So what I can do is I can just look up in my adjacency matrix, and if, let's say, if and if there's 0, then we can say that there's not an edge between these two nodes. But let's say we have our adjacency list, right? So how do you denote it? Again, consider the nodes, right? And what we'll do is we just look at the graph. There's an edge between 1 and 2 and 1 and 3, right? So what we can do is we can just push these values here like this, right? For 2, 4, and 5, right? For 3, again, it's just 1, right? So I can just push 1. Again, for 4, just 2. And for 5 also, just 2, right? So you can just intuitively look at both of these notations that the adjacency matrix consumes a lot of space when we want to represent a graph or a tree, right? And the adjacency list does not consume a lot of space. So there's this one major difference between them, right? But again, if somebody asks me the same question to check, and if I have represented my graph using this method, right, then I cannot tell them at one instance. I have to check for each node, and I have to iterate through the list to check whether there's an edge between these two nodes. So there's this difference, right? So let's say just talk about the time complexity, right? So as I was talking about traversing the graph, so like just before knowing how to traverse them, I'll just say that the adjacency matrix, right? Uh, so consider there are v number of vertex, right? And e number of edges, right? And considering that v is equal to e for some case, right? So the adjacency matrix consumes a lot of space, as well as if you want to traverse the whole graph, then it will take this much time. And if we talk about our list, then it's just v plus e. It's just v, right? I hope you guys know about the time and space complexities, like what are the terms, okay? I assume that. Okay, now let's see. So there's this one method known as DFS, and another is BFS. So what is this? This is nothing but depth first search, right? Not writing whole thing. And this is breadth first search. So let's consider my graph like this, right? Now, if I want to traverse this graph using the first method, that is DFS, and let's say I'll start from this node, right? This node. So there are two possible ways in which I can traverse during DFS. As the name suggests, the name is depth first search. So we'll go into the depth for each of the iteration. So what I'll like just see, okay. So what will happen is if we start iterating from this node, it can either go to this or this, right? So let's just assume it goes into the left side, right? So we'll go here, then it will again go down to its child, and it will go until there's like until you found a leaf. There's no node beyond that. Then what we'll do is it will again iterate back, and it will then go to the unvisited nodes, right? So if you guys know a little bit of recursion, then DFS is nothing but recursion, okay? So, yeah. So before we go on to BFS, let's just do one thing. What I'll do is I will just create a adjacency list for storing the graph, okay? Let me create it globally. And I want you guys to, again, code along with me if you want. It will be pretty helpful for you also, okay? So this is nothing but my adjacency list, right? I can denote it like this using a vector of vector, okay? And you can also denote it like this. So they both are the same, okay, in C++. What I'll do is I will, okay, let's just make this graph, right? This is 0, 1, 2, and 3, okay? So because this is an undirected graph, I need to push the nodes for both the sides, right? So what I'm telling is, let's say I write like this. So what this means is that we can go from 0 to 1. Okay. Now, if I write this, that means that we can go from 1 to 0. Okay. So if there's a directory graph, I will not write this line. Okay. So there's 0 to 1, 1 to 0, then there's 0 to 2, right? And 2 to 0. And there's 1 to 3. Similarly, 3 to 1, right? Okay. Now I want to traverse this graph, right? And we saw like what is DFS. We got a very basic idea of what DFS is. I will again just show you, right? So if I'm at this node, then I can go to either of the child, right? Let's just assume I go to left. Okay. Then I'll go to this, then I will go to this, then I will iterate back. Like I will not iterate back as it will not consume any time, but I will just then start iterating from this side. Okay. So what I mean is, let's create a function called DFS, right? And let's just assume that we are starting to traverse from uh, our node 0, right? So I can just write here DFS 0, first of all, right? And what parameter can we pass here? DFS. So we are starting from a node, so we need a node at least, right? And then what we can do is, because this is our adjacency list, right? We need to traverse to all the child for this particular node, like any particular node. So I can write like auto, like I can also write integer here. Everything is same. Integer child, and I can write like this, okay? Node. So what is this loop? This loop will basically go in the list, like for 0, the nodes are 1 and 2 in its adjacency list. So it will travel 1 and 2, right? And as I told you, it's basically a recursion. So what I can do is I can again call the function DFS, right? For the child, right? So it will then go to its child and again to its child and again to its child. Again, there's not a node that is present, right? And I can just, yeah, I don't need to return anything right now. Okay. What I'll do is I'll just print the node so you guys can see like how the vertices are being printed. Now there's one issue in this, right? So let's say I'm traversing and I'm using a recursive function. So you might know that there has to be a base case to stop the recursion, and otherwise it will just go into an infinite loop, right? So let's say I have this node, right? So, and there is an edge between both the nodes. So you can basically go from 0 to 1 and again from 1 to 0. So how will my code know if I have already visited this node or not? Because then it can just go to 0 to 1, then again from 1 to 0, again from 0 to 1, right? So we can basically just create an array like this, right? And it can do like this, right? That means that each of the node is still not visited, right? And I'll just pass a condition here that if my child is visited already, I'll just continue. I will not call the recursive function, right? And here we can just do like this. So that means that we have visited this node right now, right? Okay, let's just try running. Okay. So you can see the nodes are visited in this order: 0, 1, 3, and 2. Okay, C. Uh, okay, we'll choose blue. Okay, so you can see from 0 we went to 1, right? From 1 we went to 3, and then we went to 2 directly, right? So this is nothing but DFS, all right? It's a pretty basic code for running a recursive function, okay, for a graph. Now, the second method is BFS. Let's consider the same node, right? The same graph, sorry. This is 0, this is 3, this is 1, okay, this is 3, and this is 2, right? So what happens in BFS is you are right now currently here. So what you'll do is you will go here, you will go here. So you will basically travel level wise, right? So you will basically travel to all the child first before moving ahead. And let's say there's another node here, right? So you will also travel here. Will travel here, here, and here first, and then you will go uh, beyond. For each child, you will again um, travel. So let's say I travel these three nodes. Then for this node, I will again travel this and this. For this, I will again travel this and this. So if there's a node here, I will do not travel, like this, here, and here. I'll have to travel the nodes that are in the same level first. Okay. So for doing BFS, you need to uh, know what is a queue, because we will perform the um, traversal using a queue, right? So there are basically 3 to 4 properties of queue, like you can push, you can pop, right? You can get its size, you can know whether it's empty or not. And for C++, you don't need to implement a queue by yourself. It's just present as an STL, right? So before I code, let me just, again, give an overview of how we'll do this traverse, right? So consider this graph, right? So what I'll do is I'll have my queue, right? Let's say queue. And what I'll do is I'll push my source here, right? And what I'll do is I will iterate for each of its child, right? It's the same like we did for DFS for child into adjacency list, right? So I'll be going here first. Because what I will do is I will push this node here. Let me just again number them. So I'll push this into the queue, and then I'll go here and I'll push 2 into the queue, right? And when I'm done with these things, I can pop this node from the queue. So now my queue will become 1 and 2, right? So we have basically traversed this node, and this node. We have not traversed this yet, but we'll do that. Now, this is the child of 1, right? So what we can do is we can again get this node that is in the front of the queue, right? We'll always get the node that is in the front of the queue. And for 1, we'll again do this same thing, right? And uh, we'll just push this node into the queue, right? And we'll just pop this. So it will be now 2 and 3, right? And there's like no child for this. So then just we can pop that directly. And again, for this, there's nothing. So we can just pop it. So the queue will be empty at the end again, right? This is pretty simple. We can just push this right? And we'll write if Q is not empty, right? While Q is not empty, so while this condition is true, do is we'll write node equal to Q dot front, and we can just pop the node from the front at the start also. What we'll do is we'll say for child and node, right? And if visited again, you can just continue. Otherwise, we'll push it right into our queue. We can say like visited node equal to 1, right? And again, I can just see out, right? So you can see like the traverser changed the order of the nodes that we travel. So it's now 0, 1, 2, 3. So it's 0, 1, 2, and 3, right? So this was the pretty basic thing on how to traverse the graph, right? Uh, okay. Now, uh, let's consider this graph, right? And we need to find the number of connected components in this graph. So for this graph, the number of connected components is 1 because you can reach from any node to any node in this whole component, right? But let's say I have this graph here, and then the number of component becomes 2 because these two are a separate component. We cannot reach from any of the node here from here to here. We cannot because that's not an edge, right? Similarly, we cannot go from any of the node here to here, right? So again, the number of components for this for all of these vertices is 2, right? So how do you basically find that using your code, right? So we can do it again either with DFS or BFS, right? So let's consider this is our graph and this is our second graph, right? Okay, so I can just start traversing using DFS. So I am here, then I'll go here, right? Then I'll go here. But now there's issue. I cannot directly go to here, right? There's not an edge. So what I need to do is I need to iterate for each of the nodes, right? And check if this node is not visited, right? Then I can start my traversal like the DFS or BFS from this current node, right? And I'll just mark all the nodes as visited, right? So let's say I'm here. So I will just mark this visited, and this visited, right? So this whole is my one component. And then I'll come here when I come across this node. So again, I'll mark this visited and this visited, and then this is my second component, right? So I can just increment my count and I will know the number of connected components in the graph, right? So we'll just do it in this graph only using BFS. You can also do it using DFS, okay? So my graph is 1, 0, 1, okay, and 0, 2, and we don't need this. We can, what we can do is we can do 3, 4, and like this, right? So I'll just, my graph is like this, 3, 4, 0, 1, 2, right? So 1 will be 1, 0, 1, 2 will be my one component, and 3 and 4 will be my second component, right? What I can do is, I can just copy this. I can just make another function, BFS, right? I'll paste it here. Now, what I'll do is, I will iterate for each of the node. And I'll check if this is not visited. I'll perform my BFS, right? We need to pass the node here, and I will just push the node. Let's just say integer. Let's say u. Okay, let's pass u here, so then it will get clashed. Okay, and I can just pass I. Integer connected component equal to 0, right? And what I can do is, each time I come across an unvisited node, I will just increment this, right? And I can just then return the number of connected components, right? This will always work. So let's just see. Okay, I'll just comment this. Okay. Okay, so it's 2, right? We can again see the travels. And right. So the graph travels like it went to 0, 1, 2, and then 3 and 4. The number of connected components is 2. And it's just because we saw that it went from here, here, and then it counted this as one component, then it go to here, second component, right? So this is basically how do you find the number of connected components. Now, let's say I have a graph, right? Let's consider this graph as a tree, right? This is a tree. And somebody asked me like, what is the, let's say, length of subtree having x as the root, right? So first we need to understand what is a subtree. Consider this node as a root, right? Then this will be the subtree of this root. Like we can also consider this node in the subtree, or we cannot. It's up to us, right? So let's say if just name it 0, 1, 2, 3, 4, 5, and 6. Now for x, let's say my value is 2. So for me, this will be the subtree, right? So the length of the subtree is nothing but the number of nodes in the subtree, right? And if x is either 3, 4, 5, or 6, then it will be nothing but 1, because they are the only nodes and they do not have any child, right? So how do you again do this using code? You can obviously use DFS and BFS as well, right? But what if my number, like let's say these are known as queries, right? So what if my number of queries are so large? Then I cannot always run DFS and BFS for each of the node again and again and again, right? Because it will then it will get a lot of um, it will be a lot of time to traverse again and again and again into our graph. Let's say our number of nodes are somewhere between 1 million, right? And our queries are also somewhere between 1 million. Okay, then we cannot run our DFS again and again for Q queries, right? Because it's just too long. So in this case, what we can do is we can use, like, we can store the value of each of the, let's say for X node, we can store the number of nodes it has in its subtree, right? So let's say my X is 2 right now. So the number of nodes are 2, right? And we'll count 2 as well in the subtree. So this value will be 3. So then for each of my queries, I can just directly return this value, right? But the question is how we'll calculate this value. Okay. So what we can do is we can do a DFS traversal, right? Because we know in DFS, um, it basically goes to all the nodes in this order, right? So I'll just explain you along with the code. It will be better, right? I'll just remove this for now, right? And let's come to DFS, right? So, okay, so let's say I'm starting at a node 0, right? And what I'll do is I'm at 0, I'll go to its child 1, 2, 3, like that. So this for loop is for each of the child, right? And this DFS function will be called again and again and again until there is no node left. So let's say I'm currently at the leaf node, right? I started from 0 and now I'm at the leaf node, okay? So what I can do is, because it's a type of recursion, you might know that it calculates everything from reverse. So let's say if I want to climb these stairs and I want to know the number of steps, then it will basically go to the top, right? And then it will start counting from there, like 1, 2, 3, 4. So basically the operation, whatever you do after the DFS function will be done in the reverse process. Okay, so let's say um, I'm currently at the leaf node here. Okay, so what I can do is I can assign this node a value of 1. Okay, now what the DFS function will do is it will, from here, it will then go to its parent again because there's no node in its subtree, right? So it will go here, and what I can do for this node is, let's say my X of 1 is currently 1, right? Okay. Let's say my X of 1 is currently 1, right? And I reached this from my X3, which is also 1. So what I can do is, because this one node is a parent of this third node, right? What I can do is I can just simply add the number of subtrees in uh, the third node that it had. Okay. So again, consider this. Okay, this is 1 and 3 and 4 right now. Okay, so what I'm saying is, let's say everything is 1 for now, and I go here, and then I'll have to again go here, right, before going here. So what I'll do is I'll just add the number of subtrees that this node had. Now I will go here, okay, and I'll again come back to the parent. Because it's a recursive function, it will always come back to its original state, right? So what I can do is I can again add this value into the parent, right? So now my x1 will be nothing but 3, because it will be 1 plus 1 plus 1 itself. It will be 3, right? So let's consider this like this, okay? Everything is 1 right now. And I'll traverse. I'll go here, and then I'll go here, right? Then I'll again come back here. So this value right now will be 2. Then I'll go here and come back. So this will be now 3, right? And because I have traversed this, I'll then come back here on this again, our root node. Then this value will be nothing but 4, 1 plus 3, right? We'll just add this here. And I'll go here and again come back here. This will be nothing but 4 plus 1, that is 5. As you can see, there are 1, 2, 3, 4, and 5 nodes, right? In this subtree. We can easily do this in this way, right? So what I need to do is I can just simply write integer subtree, right? And like this, right? And what I'll do is I'll say subtree of node. That is my current node, right? What I'll do is I'll just add subtree of the child. That's it. And for each node, I can just say it is equal to 1, right? And let's say we want this 3, right? So it's 0, 1, 2. Okay. This is, let's just number them 0, 1, 2, 3, and 4. So it's 0 and 1, 0 and 2. Okay. And then it's 1, 3, and 1, 4. Right? 1, 3, and 1, 4. Right? So I'll just remove this again, and I'll just run this DFS right now, right? And we can just print it. Okay. So it's running. Okay. Now, from this figure, we can see that the number or the length of the subtree with node value 1 is nothing but 3, right? So what I'll do is subtree of 1, right? I need to know the length, right? So it's 3, you can see, right? So in this way, we can calculate the number of nodes in a particular subtree. This is also a very important concept that you have to use. It can basically come in an interview or anything like that, right? And because we don't have much time left, we can just do one more thing, which is also important. That is shortest path, right? So as I mentioned, like you are here and you want to go to your home, right? And there are several things in between, and you need to reach your home in the shortest time, right? So this is basically a concept of weighted graph, but let's just assume that for this graph, the nodes are at unit length. So the weight of each of the edge is 1, right? So what we'll do is, uh, if you observe carefully, if we perform DFS, right, then we'll go to each of the node that is like this, in this way, right? Let's say this is our home, right? And so in DFS, what will happen? It is not always that we will travel this node first or this node first, right? We can travel them in any order. It depends on how they are inputted, right? So in DFS, what will happen is you go to here, right? And then you go to here, and then you go to here. So if you maintain a count, right, then it's like 1, 2, and then 3, right? So it's wrong. Again, you can do it using DFS. There's a trick for this, but the main thing to observe was that if you visit all the childs first, right, then you are guaranteed that you will reach your home using the shortest time, because in DFS we always tend to visit the childs first, and as soon as you visit a child, you mark them as visited. So let's say even if my home is like here, but I'll always visit my child first. So I'll eventually visit this node in a count of 1, right? So basically, it will always ensure that I reach my target in the shortest or least time. So what you need to do is, um, it's pretty simple, pretty straightforward, right? What we'll do is we'll maintain, and we also assume that the graph is connected in this case, right? So we can always visit our home from any edge, right? So this is our queue, and we'll just push this 0 here, right? And what we can do is we can create a distance name variable, which will be nothing but store distance from each node. And we can basically do it like -1. So we have not reached this node yet. The distance is like, consider it as an infinite or -1. That means we cannot reach it. We haven't reached it yet. Okay. Uh, okay. So we'll perform again BFS, right? What we'll do is we'll just get our node q.front, and we can just pop it, right? And for each child, right? Now, in this case, we don't need to maintain a visited array because we are already calculating the distance. So we don't need it, right? So again, what you can do is if distance of child is equal to -1, then we can just say that distance of child will be nothing but distance of our current node plus 1, right? Because we have assumed that the node is at a unit distance from each of its parent, right? And just simply we can see out our distance of our home. So let's say it's 3 in this case, right? So we can simply return distance 3 in this way, right? So the amount of time it takes to visit home will be exactly the level that it is present from the parent, right? And because you are visiting each of the node, it can happen that your child is here, right? So in the worst case, you will just visit all the nodes, right? And then you will come across this node, like, okay, here is my node in this way, right? It's basically 3. So let's say that the number of nodes are n, then the time you took will be nothing but n plus e, the number of edges, right? So you can do this like this, and the distance of node will be 0, let's say, right? And mm, yeah, because it is a disconnected graph, it's this one. Yeah, it's this one. Yeah, this one, right? So we can just connect them. I'll just connect 0 and 3, right? Uh, hmm, This is 0 and 1, 0 and 1, 0 and 2. Okay, okay. This is one. Okay, cool. So I think we are running out of time. So basically that would be it. Again, there are a few things that you need to know before you leave, that you can uh, practice questions from Geeks for Geeks, and CS, ES problem, right? So these two things are available on the internet, and you need to basically practice the questions from very easy level, and then you can move forward with the levels that are harder than this. And again, there are again like many topics that are left. It is the articulation point, right? Then bipartite graph, right? This few of the things. I'll just share the list of topics and you can just learn them. And if you have any doubt, then you can probably ping any one of us, or you can find the solution on the internet as well, right? So I think that will be it. Uh, hmm. Okay. So the question is difference between a vector and a queue. Okay, queue is, see, if you search on the internet, queue is basically built using a linked list, right? And vector is like an array, and queue is totally different, right? So if you search like this, you will know that what is a queue and what is a vector, right? And yeah, that's the pretty basic thing. Uh-huh. And okay, how to choose BFS or DFS for shortest path, because in some cases DFS might be more shorter path. No, DFS, no, you can do it using any of the traversal, DFS or BFS. In DFS, what will you need to do is you will need to maintain a minimum variable, and you need to count like what's the um, minimum count from the parent to this node. And in that way, you can use DFS, but it's a bit, um, it's a bit lengthy and it's a bit trickier. But BFS is very simple and straightforward. So I'll suggest you can use BFS in that case. Uh, case. Other questions on Pigeonhole? Okay, there are no questions. Wow. Okay. So I think that's it. How many questions would be enough to master this topic? I mean, it depends. There is not a number. If you pick any other topic like DP or anything like that, again, it depends on person to person. But you need at least 100 questions to get started with it, right? How to choose between BFS and DFS? It's not like you need to choose. You can always go with BFS because it's straightforward. It's easier to implement it using code. You can again pick anything. The time complexity would be same only, right? But you'll always pick something that is more easier to code, right? As tags and queues as important as trees and graph. Yes, they are, because see, now we saw that queues are very important in terms of traversing graphs, right? So any question, you will need queue, right? And for stacks, I would say that, yeah, they are also important in terms of finding few things optimally, right? So let's say if you have a question where you are given graphs, right? And you are given the length of the graphs on a grid, and you need to find the area the largest area that you can get, right? So what I mean to say is, let's say uh, this is my grid and these are the graphs, right? And there are some y lengths of these graphs. So the largest area that you can get in this case would be this much, right? And in this case, it would be this much. You need maximum, right? So you can implement this using a stack. How you can order stack on the internet by yourself. But yeah, they're important. Hmm. From where did you learn graphs and trees? Uh, so I basically saw a few videos on YouTube and I'll just look at the code on Code Forces, right? If you don't know, Code Forces, it's a competitive programming platform. So yeah, but YouTube videos would be fine. You can check out videos of take you forward. Oh, share screen. Okay, shit. Yeah, so this is what I did. So you had a grade, right? And you have this like histograms type, and you need to find the maximum area that you can get. So you need to include all the histograms that are overlapping, right? So yeah. Okay, there are no more questions. I think we are done.